The universe is not just big, it's so enormous that the word big itself stops meaning anything. Today, we're going to find out exactly how large it really is, and why that answer will change the way you see everything, including yourself. Because the deeper we look into the cosmos, the more we realize the most shocking thing out there isn't a black hole, a trillion galaxies, or the edge of space and time. It's the fact that something as small as you can comprehend all of it. Before we start, if you enjoy exploring the universe with us, a quiet subscribe helps this channel reach further. Now let's begin. The whole of human civilization, every wheel ever invented, every empire ever built, every war ever fought, every scientific breakthrough ever celebrated, fits inside 1.75 seconds at the very end of December 31st. That is not a metaphor. That is pure mathematics. Take the entire 13.8 billion year history of the universe and compress it into a single calendar year. January 1st midnight, the Big Bang tears reality into existence. By mid-September, the Earth finally forms. December 30th, the dinosaurs go extinct. And then, at 23 hours, 59 minutes and 58 seconds, on December 31st, 2 seconds before the new year, the first humans appear. Everything you have ever learned in a history class. Every pharaoh, every emperor, every revolution, every invention, every moment of genius that changed the world, all of it happens in the final 1.75 seconds of that year. Ancient Rome rises and falls in a fraction of a second. The entire Industrial Revolution is over before you can blink. The internet, space travel, everything humanity has ever achieved, squeezed into a sliver of time so thin that the universe would not even notice if it disappeared. And yet here we are, asking questions about it. But that sense of smallness you are feeling right now, hold on to it, because it is about to get dramatically worse. Right now, at this exact moment, the sunlight hitting your eyes is not the sun as it is. It is the sun as it was 8 minutes ago. Light travels at 300,000 kilometers per second, the fastest thing in the universe. And it still takes 8 minutes to cross the 150 million kilometers between the sun and your eyes. Which means if the sun silently vanished right now, you would not know for another 8 minutes. You would sit there completely unaware watching a ghost. Think about that. You have never actually seen the sun in real time. Not once in your entire life. Now look up at the night sky. That pinpoint of light, you see the brightest star visible to the naked eye in the northern sky, a star called Deneb. Its light has been traveling for roughly 2,400 years to reach you tonight. When that light first left its source, ancient Vietnamese ancestors were building the early foundations of what would become a nation. The Han dynasty had not yet existed. The Roman Republic was still young, and that light has been crossing the void of space ever since, all the way to this moment to your eyes right now. You are not looking at a star. You are looking at a 2,400-year-old photograph of a star, and you have no idea what that star looks like today because today has not reached you yet. Here is where it becomes truly disorienting. Every single star in the night sky is showing you a different moment from the past. The star closest to our sun, Proxima Centauri, shows you 4 years ago. A star 200 light-years away shows you 200 years ago. A star 10,000 light-years away shows you 10,000 years ago. All of them visible simultaneously. All of them from completely different points in history. All of them painting the same sky above your head right now. The night sky is not a photograph. It is a museum. A living, breathing museum where every exhibit is frozen at a different moment in time and none of them are showing you the present. And that telescope sitting in an observatory somewhere, the more powerful it is, the further back in time it sees. The James Webb Space Telescope, the most powerful eye humanity has ever built, can see galaxies as they existed over 13 billion years ago, when the universe was less than 400 million years old. We point it at the sky, and we are watching the universe as a newborn infant. In space, looking far and looking into the past are the exact same thing. Every telescope ever built is a time machine. The most powerful telescope is the most powerful time machine, and the further we look, the older the image, until eventually we are staring at the very edge of what is visible at light that has been traveling toward us since almost the very beginning of everything. So when someone asks how big the universe is, what they are really asking is something far stranger. They are asking how far back in time can we see? How deep into the past can our instruments reach? Because out there the past is not gone, it is still arriving. So here is a question worth sitting with for a moment. If you could teleport instantly to any point in the universe, right now, anywhere at all, where would you go? And what do you think you would actually find when you got there? Your answer might change completely by the time this story is done. Because the nearest thing to us in the universe, our own cosmic neighborhood, is already enough to shatter every concept of distance the human brain was ever designed to handle. Let us try something. Imagine the sun shrunk down to the size of a basketball. You place it right in the center of a large stadium. Now, where is the Earth? The Earth at that scale is a grain of sand. A single grain of sand sitting 25 meters away from the basketball. That is it. That is the entire distance between our planet and our star, scaled down to something you can walk. Where is Jupiter, the largest planet in our solar system? A marble about 130 meters away from the basketball. Saturn, with all its famous rings, is another marble, a bit further out. Neptune, the outermost planet, is a small pea sitting 1.5 kilometers from the basketball. And the edge of our solar system, that is 6.5 kilometers away. 6.5 kilometers of almost entirely empty space, with a basketball at the center and a few tiny specks of dust and rocks scattered throughout. That is our solar neighborhood. That is the entire cosmic territory every human being who has ever lived has called home. Now forget the model and go back to real numbers. The distance from Earth to the Sun is 150 million kilometers. If you got in a car and drove at 120 kilometers per hour without ever stopping, no sleep, no fuel, no brakes, it would take you 142 years to reach the Sun. Your great-great-grandchildren would be the ones to arrive. Want to drive to Pluto? Pack more carefully. That journey would take over 5,000 years at highway speed. The Egyptian pyramids were being built 5,000 years ago. You would have needed to start driving back then to arrive at Pluto today. And yet humanity did something extraordinary. In 1977, we launched a spacecraft called Voyager 1. It left Earth traveling at 61,000 kilometers per hour, far faster than any car, faster than a bullet, faster than almost anything humans have ever built. It has been flying continuously for 46 years without stopping. And in 2012, it finally crossed what scientists consider the boundary of the solar system, the point where the sun's influence fades and interstellar space begins. 46 years of non-stop travel at 61,000 kilometers per hour just to reach the edge of our own backyard. But here is the thing nobody talks about. That boundary Voyager crossed, it is not actually the real edge of the solar system. Not even close. The true boundary is something called the Oort cloud, a vast, distant shell of icy objects that still technically orbit our sun, still falls under the sun's gravitational influence. And the Oort cloud is not a few billion kilometers away. It is roughly 1 light year away. 1 entire year of light, traveling at 300,000 kilometers per second. Voyager 1, flying at 61,000 kilometers per hour, will not reach the inner edge of the Oort cloud for another 300 years, and to fully pass through and exit the other side, 30,000 years. 30,000 years of continuous flight before that spacecraft is genuinely, truly, finally free of our solar system. We talk about Voyager leaving the solar system like it is a finished achievement, like a ship that has sailed out of harbour. But in the language of actual astronomy, that ship is still in the harbour. It has barely moved away from the dock. It is a little like telling everyone you have left your hometown, when in reality, you have just stepped outside your front door and are standing on the porch. The city is still completely around you. You have not gone anywhere. Now here is something that will quietly reframe everything. Right now, as you read this, the solar system is moving. Not drifting, gently screaming through space at 828,000 kilometers per hour, orbiting the center of the Milky Way galaxy, 700 times faster than a bullet, and even at that incomprehensible speed, completing one full orbit around the galactic center takes 225 million years. The last time the solar system was in this exact position in the galaxy, the first dinosaurs had not yet appeared. Mammals did not exist. The continents look nothing like they do today. We have completed less than one full lap around our galaxy in the entire history of complex animal life on Earth. So, which of the 8 planets in our solar system do you think is most likely to hold traces of life beyond Earth-Mars, with its ancient river valleys, or perhaps the liquid ocean buried beneath the ice of Europa, one of Jupiter's moons? Give that some thought. Because everything we just covered, every kilometre every year, every staggering distance, is still just one grain of sand. One tiny, unremarkable speck in a beach so vast you cannot see where it ends. What comes next will make the solar system feel like a small room in a house you never knew existed. Here is a thought experiment. Take the entire Milky Way galaxy and shrink it down until it fits inside the territory of Vietnam. Every mountain range, every coastline, all 330,000 square kilometers of it, that is your galaxy now. Where is the solar system in that picture? It is not visible. Not because it is small on the map, but because at that scale the entire solar system, the sun, all 8 planets, the vast emptiness between them, the Oort cloud stretching 1 light year in every direction, shrinks down to the size of a single dust molecule. Something you cannot see with your naked eye, something that would vanish if you breathed too close to it. That is our home. A speck of dust inside a country-sized galaxy. The Milky Way stretches 100,000 light-years from one side to the other. Light traveling at 300,000 kilometers per second needs 100,000 years to cross it. If ancient humans had somehow managed to send a beam of light from one edge of our galaxy, the moment they first learned to use fire, that light would still be traveling today. It would not arrive at the other side for another 97,000 years. Inside that space, there are somewhere between 200 and 400 billion stars. The uncertainty in that number alone is staggering. We are not sure whether there are 200 billion or 400 billion, and the difference between those two estimates is 200 billion suns. But even the lower number is almost impossible to hold in your mind. 400 billion stars is more than the total number of grains of sand on every beach and every desert on the surface of the entire Earth. Every grain of sand from every coastline, every dune, every desert basin on this planet, and the Milky Way still has more stars. Now here is the part that quietly puts us in our place. We like to think of Earth as special, central somehow, important. But look at where we actually are. Our solar system sits on a minor spiral arm called the Orion Arm, located about 26,000 light-years from the center of the galaxy. Not at the center, not at the outer edge, not in any particularly notable region at all. We are in a completely ordinary, unremarkable corner of a mid-sized spiral galaxy. If the Milky Way were a city, we would not be downtown. We would not even be in an interesting suburb. We would be somewhere in the middle of a quiet residential street that nobody has any particular reason to visit. And at the actual center of the city, something extraordinary and terrifying is waiting. Lurking at the heart of the Milky Way is a supermassive black hole called Sagittarius A star. It weighs 4 million times more than our Sun, 4 million suns worth of mass compressed into a single point in space, so dense that not even light can escape its grip. If you replaced our Sun with Sagittarius A star, it would swallow Mercury, Venus, Earth, Mars, and extend halfway to Jupiter without even noticing. Our entire world would simply cease to exist, consumed without so much as a ripple. And that is just the black hole sitting at the center of one average galaxy. Now imagine you wanted to have a conversation with someone on the other side of the Milky Way. You send a radio signal traveling at the speed of light, the fastest possible speed anything in the universe can move. That signal leaves Earth right now. Your great-great-grandchildren are born, live full lives, and die. Entire civilizations rise and fall. 100,000 years pass. And your signal is still traveling. It has not arrived yet. After 100,000 years, the signal finally reaches the other side. And if against all odds someone is there to receive it and immediately sends a reply, that reply will not reach Earth for another 100,000 years, a 200,000-year round trip. For a single exchange of words, we send messages to each other across the world in fractions of a second and call it instant communication. Across a galaxy, the concept of conversation becomes something almost philosophical. But the Milky Way, for all its overwhelming scale, is not even a particularly large galaxy. There are galaxies out there that make ours look embarrassingly small. One of them, a galaxy called IC1101, is roughly 50 times larger than the Milky Way. It contains more than 100 trillion stars. That number 100 trillion is larger than the total number of cells in the bodies of every single human being alive on Earth today combined. One galaxy. More stars than all the cells in all the people on this planet. And even that is just one galaxy among countless others. Then there is this: the Milky Way is not staying still. Right now our galaxy is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbour. The two of them are hurtling toward each other at 110 kilometers per second. In approximately 4.5 billion years, they will collide and begin a slow, spectacular merger that will last for billions of years. But here is the part that surprises most people. When two galaxies collide, almost nothing actually hits anything else. The distances between individual stars are so enormous that the two galaxies will pass through each other like two clouds of smoke drifting together. Stars will be flung into new orbits. The shapes of both galaxies will be completely transformed. A new combined galaxy will slowly take form over billions of years. But actual stellar collisions, almost none. It is a collision of immense cosmic structures where almost nothing physically touches. A catastrophe in slow motion reshaping 200 billion stars without destroying a single one. Which raises an interesting thought. Right now, somewhere in the Andromeda Galaxy, there may be civilizations looking back at us, watching the Milky Way growing larger and brighter in their sky over millions of years, knowing exactly what is coming. Do you think they know? And if they do, what are they doing about it? 400 billion stars in one galaxy is already enough to break every scale of measurement to the human mind uses. But here is what you need to hold on to as we move forward. The Milky Way is just one of 2 trillion galaxies in the part of the universe we can actually see. 2 trillion galaxies. And that word observable is where everything starts to get truly, genuinely strange. Picture a sphere. You are at the center. In every direction, as far as any instrument humanity has ever built can possibly detect the universe, stretches outward for 46.5 billion light years. That sphere, that bubble of space surrounding Earth in every direction, is what scientists call the observable universe. And right away, something about that number should bother you. The universe is 13.8 billion years old. Light travels at a fixed speed. So logic says the furthest we should ever be able to see is 13.8 billion light years, the distance light could have traveled since the very beginning. But we just said the observable universe reaches 46.5 billion light years in every direction. How is that possible? The answer is one of the strangest things about the cosmos. Space itself has been expanding the entire time. When light left a distant galaxy 13 billion years ago and began its journey toward us, the universe was already stretching outward in every direction. The galaxy that sent that light has been carried further and further away by the expansion of space itself, even while its light was still traveling. By the time that light finally reaches our telescopes, the galaxy that sent it is now much, much further away than it was when the light departed. So the observable universe is not a sphere showing us where things are now. It is a sphere showing us where things were at various points in the past when the light we are receiving today first left them. Distance and time are folded together in a way that quietly dismantles every intuition about how space is supposed to work. The most distant galaxy ever observed by human instruments had its light travelling for 13.4 billion years to reach us. When that light left its source, the universe was only 400 million years old. Young, hot, chaotic. The structures we see today, the orderly spiral galaxies, the stable solar systems, the slow cosmic architecture, none of that existed yet. We are looking at the universe as a newborn, raw and unformed, in the first moments after the fires of creation began to cool. And somewhere in that ancient distant light is the faintest whisper of an even earlier signal. 380,000 years after the Big Bang, the universe had cooled just enough for the first atoms to form. In that moment, light was able to travel freely for the first time. That light is still moving through space today, stretched by billions of years of cosmic expansion into microwave radiation, arriving at us from every direction simultaneously. Scientists call it the Cosmic Microwave Background CMB. It is the oldest light in the universe. The literal afterglow of creation, still faintly glowing at 2.7 degrees above absolute zero, filling all of space like a whisper that has never stopped echoing. Every time a radio telescope picks up that signal, It is hearing the voice of the universe from before stars existed. Now take everything you just absorbed, the distances, the timescales, the 2 trillion galaxies within our observable bubble, and hold it against this one image. In 2022, the James Webb Space Telescope released its first deep-field photograph. To take it, the telescope pointed at a patch of sky so small that if you held a grain of sand at arm's length, that grain of sand would cover the entire region being photographed. A piece of sky smaller than a grain of sand. In that photograph, thousands of galaxies, each one containing hundreds of billions of stars. Some of them so distant that their light had been traveling for over 13 billion years just to reach the lens of that telescope. All of it, this incomprehensible abundance of suns and worlds and cosmic history, packed into a speck of sky, too small to see, without holding something up to block it. Point the telescope at any other direction, any random patch of apparently empty darkness. You will find the same thing. Thousands of galaxies, every direction, every patch. The universe is not sparse. It is overwhelmingly, almost offensively full. But here is where the story takes a turn that has nothing to do with what is far away. It has to do with what is permanently, irrevocably beyond reach. The cosmic horizon is not a wall. There is no physical boundary out there, no barrier you could approach and press your hand against. It is something far stranger, a causal limit. Beyond a certain distance, space is expanding so fast that light from those regions can never reach us no matter how long we wait. Those regions are not just far away, they are causally disconnected from us. Events happening there cannot influence anything here, ever, in any way, under any circumstances. And right now, while you are reading this, galaxies are crossing that horizon, permanently. Galaxies that we can see today that our telescopes can currently observe are being carried beyond the edge of what we can ever know by the accelerating expansion of space. Not destroyed, not gone from the universe. Simply gone from our universe, slipping past the horizon like ships sailing beyond the curve of the ocean. Except the ocean keeps curving faster and faster, and those ships are never coming back. Every single day, more of the universe becomes permanently invisible to us. The cosmos is not just large, it is actively shrinking, not in size, but in the portion we will ever be able to access or know anything about. Which raises a question worth genuinely sitting with. If there is a civilization somewhere beyond our cosmic horizon, a civilization that has perhaps been trying to reach us for millions of years, building transmitters larger than planets, broadcasting signals containing everything they know about the universe, would we ever receive a single word? Would they even know their messages could never arrive? 2 trillion galaxies in the observable universe is already a number that defeats comprehension. But everything we have seen, everything our instruments have ever detected, everything humanity has ever learned about the cosmos, all of it sits inside this one bubble of observable space. What lies beyond it is not empty, it is simply permanently forever out of reach. And out there beyond the horizon, every familiar rule of mathematics and physics begins to collapse in ways you are not prepared for. We have mapped 2 trillion galaxies. We have measured the observable universe at 93 billion light-years across. We have found the oldest light in existence and traced the structure of cosmic filaments stretching hundreds of millions of light-years. It feels for a moment like we have some grip on the size of things. That feeling is an illusion, and it is about to be dismantled completely. The most conservative estimate in modern cosmology, not the wild speculation, not the fringe theory, but the careful, sober, peer-reviewed lower bound that mainstream scientists are comfortable defending, is that the actual universe is at least 250 times larger than the part we can observe. That gives a diameter of roughly 23 trillion light-years, 23 trillion. A number so large that the observable universe, with all its 2 trillion galaxies, fits inside the real universe the way a single marble fits inside a city. And here is the part that should make you deeply uncomfortable. That 250 times estimate might itself be a colossal underestimate. Some models suggest the true universe could be millions of times larger than what we see. Others suggest it could be genuinely mathematically infinite. We do not know, we cannot know. Because by definition, everything beyond our cosmic horizon is permanently invisible to us, no matter how powerful our instruments become or how long we wait. we are not looking at a map with unexplored regions at the edges. We are looking at a map that only shows the interior of one small room with no way of knowing whether the building around it has 10 rooms or 10 billion, or no walls at all. To understand how this happened, how the universe got so incomprehensibly large, you have to go back to the very first moment of existence. Not the first second, not the first millisecond, the first 10 to the power of negative 32 seconds after the Big Bang. A unit of time so small, it has no name in everyday language, a sliver of a moment, so brief that no clock ever built or imagined could measure it. In that unmeasurable instant, something happened that physicists call cosmic inflation. The universe did not simply expand, it detonated. Space itself stretched at a rate that makes every other kind of growth look completely stationary by comparison. In that single, unimaginable flash, the universe grew from something smaller than a single proton, smaller than the smallest thing physics can meaningfully describe, to roughly the size of an orange. That does not sound dramatic until you think about the scale of what happened. A proton is approximately 1 femtometer across. An orange is approximately 8 centimeters across. The ratio between those two sizes is roughly 10 to the power of 14. The universe expanded by a factor of 100 trillion in a fraction of a moment, faster than light, far faster. Space itself was stretching so quickly that the speed limit of light was entirely irrelevant. Nothing was moving through space. Space itself was growing. And the consequence of that explosion is the universe we cannot see. All that space generated in that fraction of a moment, flung outward beyond any horizon we could ever observe, exists right now, full of matter, full of structure, full of whatever physics produced in those regions and permanently beyond our reach. But within the part, we can observe something remarkable emerged from all that expansion. As the universe cooled and gravity began pulling matter together over hundreds of millions of years, a structure formed that no one predicted, and that still produces a quiet sense of awe in everyone who sees it for the first time. Scientists call it the cosmic web. Imagine the largest spider's web ever conceived. Now imagine each thread of that web is not a strand of silk, but a filament of dark matter and gas, hundreds of millions of light years long. And where the threads intersect, there are not drops of dew, but clusters of thousands of galaxies, each cluster containing more stars than there are grains of, sand on Earth. Now imagine that web stretching across the entire observable universe in every direction, three-dimensional and vast beyond description. That is the cosmic web, the largest known structure in the universe. And when you see it mapped out by supercomputers using data from millions of galaxy observations, the first thing most people notice is how alive it looks, how organic. The filaments branching and connecting, the dense nodes glowing at the intersections, the vast empty voids between the threads. It looks almost exactly like a photograph of neurons in the human brain. The resemblance is not poetry. Researchers have measured it mathematically and found the structural similarities are striking in ways that are still being studied. Sitting within one corner of this web is a structure that contains our home. Scientists named it Laniakea, a Hawaiian word meaning immeasurable heaven. The Laniakea supercluster is the large-scale structure in which the Milky Way resides, along with approximately 100,000 other galaxies, all loosely bound by gravity in a region of space 520 million light years across. 520 million light years. Light crossing from one edge of Laniakea to the other takes more than 500 million years. The entire history of complex animal life on Earth, from the first fish to the last human who will ever live, would not be enough time for that light to complete the journey. We are not guests in Laniakea. We are something far smaller and more temporary than the word guest implies. And Laniakea itself is being pulled. Everything in it, every one of those 100,000 galaxies, including ours, is being dragged through space towards something that we cannot see directly. The gravitational influence is undeniable. The Milky Way is moving toward it at 2.2 million kilometers per hour, and thousands of other galaxies are doing the same, all converging on the same point from every direction. Scientists call it the Great Attractor. It lies in a region of space directly behind the densest part of the Milky Way's disk, hidden behind billions of stars and clouds of gas and dust that block our view in visible light. We know it is there because its gravitational fingerprint is written across the motion of everything around it. We can calculate its approximate mass. We can map the direction of the pull, but we cannot see it with our own eyes. Not yet. Something enormous is drawing us toward it, and an entire galaxy stands in the way of us getting a clear look. Now take all of this, the cosmic web, Laniakea, the great attractor, the true universe, 250 times larger than what we can observe, and follow the mathematics to its logical end. If the universe is truly infinite in extent, then the number of possible arrangements of atoms is finite. There are only so many ways you can arrange the atoms in a human-sized volume of space. Once you have run through every possible arrangement, the configurations must repeat. Which means somewhere at a distance of approximately 10 to the power of 10 to the power of 29 meters from where you are sitting right now, there is a perfect atomic copy of you. Same atoms, same arrangement, same memories, same thoughts, same everything. Reading this exact sentence at this exact moment, not as a philosophical possibility, as a mathematical inevitability, but only if the universe is truly infinite. The mathematics does not suggest it, it demands it. And that is where infinity stops being a large number and starts being something that quietly destroys every framework your brain uses to process meaning and probability. In an infinite universe, probability itself ceases to function the way we expect. If every possible event happens infinitely many times, then nothing is rare, nothing is special, nothing is improbable. Everything, including things that seem impossible, happens somewhere infinitely often. The concept of something being unlikely requires a finite space to be meaningful. Take away the finite space, and you take away the concept itself. So here is the question to sit with before we go further. Which unsettles you more, the possibility that the universe is infinite and everything imaginable must therefore exist somewhere, or the possibility that we might never know whether that is true? We have now mapped everything visible. We have found the edges of what light can show us and looked at what lies beyond, and what we found is that the observable universe, for all its 2 trillion galaxies and billions of light years of structure, might be nothing more than a tiny patch of something unimaginably larger. But here is what we have not talked about yet. 95% of even the observable universe is made of something that science has no choice but to call dark, simply because no one knows what it actually is. Not dark in color, dark in understanding, and that is precisely where the story stops being merely large and starts being genuinely frightening. Everything you have ever seen, touched or thought about, every star that has ever burned, every planet that has ever formed, every ocean, every mountain, every living creature, every atom of every substance that has ever been given a name, accounts for 4.9% of the total mass and energy in the universe. 4.9%. Not a majority, not even close to a majority, a rounding error. The remaining 95% of everything that exists is made of things that have never been directly detected, never been captured, never been examined in a laboratory, and never been explained in any satisfying way by any physicist alive today. We know they are there. We can measure their effects with extraordinary precision. But what they actually are at a fundamental level remains one of the deepest unsolved mysteries in all of science. The first of these unknowns makes up 27% of the universe. Scientists call it dark matter, not because it is dark in color or because it absorbs light, but because it is invisible to every instrument we have ever built that detects electromagnetic radiation. It does not emit light. It does not reflect light. It does not interact with light in any way we can measure. It passes through ordinary matter almost entirely without effect, as though the two simply do not notice each other. And yet, it is everywhere, wrapped around galaxies like an invisible scaffolding. Woven through the cosmic web in filaments we can only map indirectly, holding the entire large-scale structure of the universe together from the inside out. The evidence for dark matter is not subtle. When astronomers measure how fast stars orbit the center of a galaxy, they find something that should not be possible. Stars at the outer edges of galaxies are moving far too fast. According to the laws of gravity, stars that far from the galactic center should be moving slowly, the same way the outer planets of our solar system move more slowly than the inner ones. But they are not moving slowly. They are moving at nearly the same speed as stars, much closer to the center. Something invisible, something massive, something distributed throughout and beyond the visible galaxy is providing additional gravitational pull that keeps those outer stars from flying off into intergalactic space. Without dark matter, every galaxy in the universe would have torn itself apart billions of years ago. The stars would have scattered outward, the spiral arms would have dissolved, and the beautiful structured galaxies we observe would simply not exist. Dark matter is not an exotic addition to the universe. It is the foundation the entire visible cosmos is built upon. The most striking direct evidence came from an event called the Bullet Cluster, two galaxy clusters that collided with each other hundreds of millions of years ago. When they hit, the hot gas that makes up most of the ordinary matter in each cluster slammed together, slowed down, and piled up in the middle of the collision, glowing in X-rays that our telescopes can detect. But the dark matter in each cluster did something completely different. It passed straight through the collision, barely interacting at all, continuing onward as if the other cluster was not even there. The two components separated cleanly. Ordinary matter in the middle, dark matter sailing past on both sides. It was the clearest visual proof that dark matter exists and that it is genuinely different from everything else we know. Not a modified theory of gravity, not a miscalculation. Something real, something massive, and something completely unlike anything in the standard model of physics. Then there is the second unknown, 68% of the universe, something called dark energy. In 1998, two independent teams of astronomers were studying distant supernovae stellar explosions so bright they can be seen across billions of light years to measure how fast the universe was expanding. Everyone expected to find that the expansion was slowing down. Gravity pulls things together so naturally, the mutual gravitational attraction of all the matter in the universe should be putting the brakes on the expansion over time. What they found instead stopped both teams cold. The expansion was not slowing down, it was speeding up. Something was pushing space apart. Not just overcoming gravity, but actively accelerating the separation of everything from everything else, growing stronger as space grew larger, filling the void with energy that seemed to appear from nowhere and intensified as the universe expanded. It was one of the most unexpected discoveries in the history of science, and it earned the Nobel Prize in Physics in 2011. Over 25 years later, the fundamental nature of dark energy remains completely unknown. There is something quietly amusing about the situation if you step back far enough to appreciate it. The two most dominant components of the entire universe, together making up 95% of all that exists, have been given names that are essentially scientific admissions of defeat. Dark matter, dark energy. Not descriptions of what these things are, but honest acknowledgements that we cannot see them and have no idea what we are dealing with. It is the equivalent of a physicist standing in front of a whiteboard, writing the words "something is here, doing something," and then publishing that as a serious scientific paper, which is more or less what happened, and it won a Nobel Prize, deservedly. But dark energy is not merely mysterious, it is dangerous on cosmic timescales. Right now, dark energy is causing the expansion of space to accelerate steadily. Galaxies are drifting apart faster and faster. If that acceleration continues and intensifies, physicists have described a scenario they call the Big Rip. First, the accelerating expansion overcomes the gravity, holding galaxy clusters together, and the clusters dissolve. Then, individual galaxies are torn apart as space expands faster than their internal gravity can compensate. Then, solar systems. Then, planets. Then eventually, even atoms themselves. The bonds holding nuclei together, ripped apart by the expansion of the space between subatomic particles. In approximately 20 billion years, if dark energy continues on its current trajectory, every structure in the universe down to the subatomic level would be destroyed, not gradually faded, torn apart. And even if the Big Rip never comes, even if dark energy stabilizes or weakens, the universe is still heading somewhere that offers no comfort. A state physicists call heat death. The point of maximum entropy when every temperature difference in the universe has been equalized, when no reaction can happen, no work can be done, no information can be processed. A universe of perfect, permanent, absolute stillness. Not destroyed, just finished. If you could somehow understand dark energy well enough to harness it, to tap into the force that makes up 68% of all that exists and is currently accelerating the expansion of space itself, what do you think that would mean for human civilization? What would become possible? We, have spent this entire journey so far building a picture of a universe that is vast, ancient, and mostly invisible. 95% of it is beyond our understanding. But even the 5% we think we understand operates according to rules so strange that every intuition about how space should work turns out to be completely wrong, because space is not a container holding the universe. Space is the universe. A living, breathing, bending, rippling entity that does things no container has ever done, and it is doing them right now all around you, whether you can feel it or not. For most of human history, space was assumed to be a backdrop, a fixed, empty, invisible stage on which the universe performed. Planets moved through it, stars burned within it, galaxies drifted across it, but space itself did nothing. It was simply there, passive, unchanging, infinite, and inert. Albert Einstein ended that idea permanently in 1915. His general theory of relativity replaced the backdrop with something far stranger and far more interesting. Space and time, Einstein showed, are not separate things. They are woven together into a single four-dimensional fabric called spacetime. And that fabric is not fixed. It is physical. It has shape. It can be bent, stretched, compressed, and made to ripple by mass, by energy, and by the movement of massive objects through it. The consequences of this are so counterintuitive that even a century after Einstein published his equations, they still feel like science fiction every time you encounter them. Start with something familiar. The Earth orbiting the Sun. We learn in school that gravity is a force that the Sun pulls on the Earth across the vacuum of space, keeping it in its circular path. But that is not actually what is happening. What is happening is that the Sun, by virtue of its enormous mass, curves the space-time fabric around it. The Earth is not being pulled by a force in the way a string pulls a ball. The Earth is following the straightest possible path through a curved landscape. It is doing the cosmic equivalent of rolling along the inside of a curved bowl, and the curvature of the bowl is caused by the Sun sitting at the bottom of it. Gravity is not a force reaching across space. Gravity is the shape of space itself. Now follow that logic somewhere more extreme. A black hole is what happens when an object becomes so dense that it curves space-time infinitely. Not a lot, not severely, infinitely. The curvature at the center of a black hole, the singularity is complete and total. And because light follows the curvature of space-time just like everything else, light that travels into that region finds that every path through space, no matter which direction it points, curves back inward. There is no outward direction anymore. The geometry of space itself has been so thoroughly distorted that escape is not merely difficult. It is geometrically impossible. You might think this is a purely abstract idea with no practical relevance. It is not. The GPS application on your phone works because a network of satellites in orbit around Earth broadcasts precise time signals that your phone uses to calculate its position. But here is the problem. Those satellites are moving fast and sitting high above Earth's surface, where gravity is slightly weaker than at ground level. Both of those factors, speed and gravitational field strength, affect the rate at which time passes exactly as Einstein's equations predict. Time runs slightly faster for the satellites than it does on the ground. If the GPS system did not continuously calculate and correct for this difference, the positional errors would accumulate at a rate of roughly 10 kilometers per day. Your navigation app would be useless within hours. Every time you use GPS, you are depending on relativistic physics to give you an accurate answer. Einstein's abstract theory of curved spacetime is built into the infrastructure of modern life. Now push further. At the edge of a black hole, the boundary called the event horizon, the time dilation is not slight, it is extreme. An astronaut hovering just above the event horizon of a sufficiently large black hole would experience time at a rate so much slower than an observer far away that a single hour at the horizon could correspond to thousands of years. Elsewhere, this is not a feeling of time passing slowly. It is not a psychological illusion. The actual physical rate of time passage is different. Clocks run slower, atoms vibrate slower, every physical process unfolds slower. Time itself is genuinely, measurably, verifiably different from one location to another. And space-time does not just bend, it rings. In September of 2015, instruments detected something that had been predicted by Einstein 100 years earlier, but never directly observed. Two black holes, each one dozens of times more massive than our Sun, had been spiraling toward each other for millions of years, somewhere 1.3 billion light-years away. When they finally collided and merged, they released an enormous burst of energy in the form of gravitational waves, ripples in the fabric of space-time itself, expanding outward from the collision at the speed of light in every direction. When those waves reached Earth after traveling 1.3 billion light-years, they caused every ruler, every atom, every distance in the entire detector to stretch and compress by an amount smaller than 1,000th the diameter of a comet. Single proton. Smaller than anything that had ever been measured before in the history of science, and the instruments caught it. The universe had spoken, and humanity for the first time had ears sensitive enough to hear it. Then in 2019, something that had been theorized for decades was finally seen directly. A radio telescope network spanning the entire Earth combined its observations to produce the first image of a black hole. Not an illustration, not a simulation, an actual photograph. The target was a black hole at the center of a galaxy called M87, located 53 million light-years away. That black hole is wider across than our entire solar system. It weighs 6.5 billion times more than our Sun. The image showed a bright ring of superheated gas glowing around a perfectly circular shadow, the silhouette of an event horizon cast against the light of everything falling into it. The largest single object ever photographed. The most extreme distortion of space-time ever directly observed. And it looked exactly like Einstein's equations said it should. If you could observe a black hole consuming a star from a safe distance, watching the star stretch and elongate as it approaches the event horizon, watching light bend around the darkness, watching the final moments of something enormous, to disappear past a boundary, it can never return. From what do you think that experience would feel like? Space bends, time slows, light is imprisoned. And all of that, every strange, disorienting, counterintuitive fact, sits within the 5% of the universe that physics can actually describe. The other 95% is dark and unknown, but even within the known, something far stranger is waiting. Because the deeper you look into the structure of reality, the more unavoidable a single question becomes: is this universe the only one? We ended the last part with a question. Is this universe the only one? It is the kind of question that sounds like pure philosophy, the sort of thing debated in late-night conversations with no real answer expected. But in the last few decades, that question has migrated from philosophy into physics, and the answer that the mathematics keeps pointing toward is deeply unsettling. To understand why, go back to cosmic inflation, that period of impossibly rapid expansion in the first fraction of a second after the Big Bang. Inflation solved several problems in cosmology that had no other clean explanation. It explained why the universe looks the same in every direction. It explained the flatness of space on large scales. It explained the distribution of galaxies we observe today. The evidence for inflation is compelling enough that most cosmologists accept it as the best available description of the universe's earliest moments. But inflation comes with a consequence that its creators did not initially anticipate, and that many physicists find deeply uncomfortable to accept. According to the best current models, inflation did not stop everywhere at the same time. It stopped in our region of space, and that stopping created the conditions for our universe to form. But in most other regions of space, inflation never stopped. It is still happening. Right now, beyond any horizon we could ever observe, space is continuing to expand exponentially in all directions, endlessly generating new volume, endlessly pushing outward, with no mechanism to halt it. This is what physicists call eternal inflation, and it has a mathematical consequence that follows as inevitably as any equation in science. When inflation stops in a region, that region collapses into what physicists call a bubble universe, a self-contained pocket of space with its own physical properties, its own history, its own Big Bang. Our universe is one such bubble. And if inflation is eternal and ongoing everywhere outside our bubble, then the process of bubble formation never stops either. New bubble universes are constantly nucleating out of the inflating background, the way bubbles form in boiling water. Except the water never stops boiling, and the bubbles never stop forming. The result is a multiverse, not one universe, but an uncountable, possibly infinite collection of separate universes, each one a bubble floating in an eternal sea of inflating space, each one completely causally isolated from all the others. No signal, no light, no particle, no information of any kind can travel between them. They are as separate from each other as things can possibly be. And here is where it becomes genuinely strange. The physical constants that define how our universe works, the strength of gravity, the mass of the electron, the strength of the nuclear forces, the value of dark energy, are not necessarily fixed universal values. They may be determined by the specific conditions under which each bubble universe formed, the way the outcome of a chemical reaction depends on temperature and pressure. Different bubbles, different conditions, different constants. In some bubble universes, gravity is slightly stronger than in ours. Strong enough that matter collapses into black holes before stars can ever form. No stars means no nuclear fusion, no heavy elements, no planets, no chemistry complex enough for life. In other bubbles, the nuclear force is slightly weaker, and atomic nuclei cannot hold together. Hydrogen exists, but nothing heavier can form. No carbon, no oxygen, no possibility of molecules, let alone living organisms. In still others, dark energy is so strong that space expands too fast for matter to ever clump together at all, and the universe remains a thin, cold, featureless gas forever. The vast majority of bubble universes in this picture are sterile, empty, physically incapable of producing anything resembling complexity. Our universe, with its carefully calibrated constants that allow stars to burn for billions of years, atoms to bond into molecules, and molecules to organize into living things, our universe is extraordinarily unusual in this landscape. Whether that is by design, by selection, or simply by the sheer statistical inevitability of infinity producing every possible combination eventually is a question that remains open. There is a second version of the multiverse that comes from a completely different direction, from quantum mechanics rather than from cosmology. In standard quantum mechanics, when a particle exists in a superposition of multiple possible states, a measurement forces it to take on one definite value. The other possibilities disappear. But one interpretation of quantum mechanics, the many worlds interpretation first proposed by Hugh Everett in 1957, says that the other possibilities do not disappear, they happen. All of them. Each possible outcome of each quantum event occurs in a separate branching universe, splitting off from ours at the moment of the measurement. Under this interpretation, every quantum event and quantum events are happening everywhere, constantly, in every atom of every object in the universe, generates a new branching of reality. The universe is not a single history, but an incomprehensibly vast tree of branching histories, every branch equally real, every possible outcome of every possible event playing out somewhere in the structure. A third type of multiverse comes from string theory and its relatives. In these models, our universe is a three-dimensional membrane. Physicists call it a brain, floating in a higher dimensional space that contains other brains as well. We cannot perceive the extra dimensions. We cannot detect the other brains directly, but they are there, moving through the higher dimensional bulk. And occasionally, over vast timescales, two brains collide. That collision generates an enormous release of energy across the entire surface of both brains simultaneously. It generates, in other words, a big bang. Our universe may be the result of just such a collision, a cosmic accident in dimensions we cannot access or perceive. All three of these multiverse models share one deeply frustrating property. They cannot be tested. By definition, other bubble universes lie beyond our causal horizon. Other branches of the quantum wave function do not interact with ours after splitting. Other brains are hidden in dimensions we cannot measure. No experiment you could design, no observation you could make, no instrument you could build would allow you to reach across and confirm that any of these other universes actually exist. This is the sharpest debate in modern theoretical physics. Some physicists argue that a theory which makes no testable predictions is not science at all, regardless of how beautiful or mathematically inevitable it appears. Others argue that if the mathematics of our best confirmed theories leads unavoidably to a conclusion, then dismissing that conclusion simply because it is hard to test is its own kind of intellectual failure. The argument is unresolved. It may remain unresolved indefinitely. But here is what is not in dispute. If eternal inflation is correct, the multiverse is not a speculation added on top of the theory. It is what the theory says. You cannot accept inflation and reject the multiverse any more than you can accept that fire is hot and reject the idea that touching it will burn you. The mathematics does not offer a middle ground, so think about it honestly. Do you believe in the multiverse? And if somewhere out there, another version of you exists, shaped by different choices, different chances, a different history, which version would you most want to know about? The multiverse is already enough to dissolve every comfortable assumption about the uniqueness of existence. But there is a theory that goes even further, one that does not just multiply the number of universes but questions whether the three-dimensional space inside any universe, including ours, is actually what it appears to be. And once you hear it, you cannot unhear it. Take a credit card out of your wallet and look at the hologram on its surface. What you see is a flat two-dimensional sticker. But tilt it under the light, and a three-dimensional image appears something with depth, with volume, with the visual properties of an object occupying space. All of that three-dimensional information is encoded on a flat surface. Nothing about the depth is real in a physical sense. It is all information projected. Now consider the possibility that the universe works the same way. The holographic principle is not a metaphor borrowed from credit card technology. It is a serious result that emerged from the mathematics of black hole thermodynamics in the 1990s, developed primarily by physicists Jacob Bekenstein and Stephen Hawking, and later formalized by Leonard Susskind and Gerard Date Hooft. What they found when they studied the properties of black holes very carefully pointed towards something deeply strange about the nature of space itself. When an object falls into a black hole, it carries information, the specific arrangement of its atoms, its quantum state, everything that makes it what it is, physically. A long-standing debate in physics concerned what happened to that information. Did the black hole destroy it, which would violate fundamental laws of physics, or did it preserve it somehow? The answer that the mathematics converged on was surprising. The information is preserved, but not inside the black hole. It is encoded on the surface of the event horizon, the two-dimensional boundary at the edge of the black hole, like data written on a screen. The entropy of a black hole, the measure of how much information it contains, is proportional to the area of its event horizon, not the volume of space inside it. This is a profound and unexpected result. For almost every other physical system, the amount of information contained in it scales with its volume. More space, more information. But for a black hole, the information scales with its surface area. The three-dimensional interior is fully described by what is written on the two-dimensional boundary. If this is true for black holes, some physicists argued it may be true for any region of space. Any volume of three-dimensional space may be fully and completely described by information encoded on its two-dimensional boundary surface. The depth, the volume, the three-dimensionality that you experience moving through space, all of it might be a projection from a flat surface, the same way a holographic image is a projection from a flat sticker. This is the holographic principle, and it is not fringe physics. It is one of the most actively studied ideas in theoretical physics today, supported by a mathematical framework called the AD-CFT correspondence, which has produced thousands of published papers and has become a primary tool for studying quantum gravity. It does not prove that we live in a hologram, but it demonstrates rigorously that a three-dimensional universe with gravity can be mathematically equivalent to a two-dimensional universe without gravity on its boundary. The two descriptions contain exactly the same information. From there, a related but separate idea follows a different path to a similarly disorienting conclusion. The simulation hypothesis asks a deceptively simple question. If a civilization becomes sufficiently advanced, if its computational power grows exponentially over centuries or millennia, as ours has already begun to do, would it eventually become capable of simulating an entire universe, complete with physical laws, with matter, with planets and stars, and with conscious beings who experience that simulated reality as genuine? If the answer is yes, then consider the statistics. A single advanced civilization running such simulations might produce thousands or millions of simulated universes. The simulated conscious beings within those universes would experience their reality exactly as we experience ours. They would have no way of knowing they were simulated. Now add up the numbers. If simulated universes can exist, there would be vastly more simulated universes than real ones, perhaps millions to one, which means the probability that any given conscious observer, chosen at random from all conscious observers that exist anywhere, is living in the one real universe, rather than one of the millions of simulations, is vanishingly small. The universe follows mathematical laws with a precision that is frankly astonishing. Not approximately mathematical, not mostly mathematical. Every physical phenomenon we have ever measured at every scale, from the behavior of subatomic particles to the rotation of galaxies, can be described with extraordinary accuracy by mathematical equations. Reality behaves exactly as you would expect it to behave if it were written in code, if the rules governing it were precise, consistent, and computational. This does not prove anything, but it is the kind of thing that once you notice it, is difficult to explain away. And there is no experiment you could design to tell the difference. Every measurement you make, every observation you record, every instrument you use to probe the nature of reality, all of it exists inside the system you are trying to examine. You are like a character inside a video game, trying to figure out whether the game is running on a computer. Every tool available to you is part of the game. The code that generates the world also generates you and your instruments and the results of your measurements. There is no outside perspective available from within. But here is the thing that deserves to be said clearly. If we are a simulation, it does not diminish anything. The love you have felt is real. The grief you have carried is real. The moments of beauty and clarity and connection that have mattered to you, they are real. Because real means experience from the inside, and you have experienced them. A simulated consciousness feeling genuine emotion is not less conscious and not feeling less genuine emotion. The experience is the thing. The substrate it runs on is secondary. If you knew with absolute certainty that you were living inside a simulation, that the stars you see were rendered geometry and the ground beneath you was calculated physics, would it change anything that actually matters to you? Would it change how you treat the people around you or what you choose? To do with the time you have, whether the universe is real or simulated, one thing cannot be argued away. Consciousness exists. Something is experiencing this. Something is asking these questions. And that fact, the bare, undeniable existence of awareness, turns out to be the strangest and most important thing in the entire story. Because the final question is not about the size of the universe, or whether it is one of many, or whether it is a projection from a flat surface. The final question is about consciousness itself and its relationship to all of this. And where that question leads is somewhere no one expected. The universe is not eternal. It was not always here, and it will not always be here. It had a beginning. It is changing right now in ways both slow and irreversible. And it will have an ending, though the form that ending takes depends on which branch of physics you follow into the future. What most people do not stop to consider is where we sit within that arc. Not at the beginning, not near the end, at the single most extraordinary moment the universe will ever produce. To understand why you need to walk the full length of cosmic time, in the first 380,000 years after the Big Bang, the universe was a place of pure, overwhelming violence. The temperature was so extreme that electrons could not bind to protons. Atoms, the basic building blocks of everything that has ever existed, could not form. Every time a proton reached out to capture an electron, the surrounding radiation immediately tore them apart again. The entire universe was a dense, opaque plasma, a fog so thick that light could not travel more than a short distance before being absorbed and re-emitted. Space was not dark. It glowed with blinding intensity in every direction, but nothing could see through it. Nothing could move through it freely. There were no stars, no planets, no structure of any kind, just an unbroken, roiling sea of energy, and particles with nowhere to go and no way to organize. Then, 380,000 years in the universe, cooled just enough. Electrons slowed down enough to be captured. The first atoms formed, and in a moment that astronomers can still detect today as the cosmic microwave background, the universe became transparent for the first time. Light streamed freely through space in every direction. The fog lifted, and the long, slow work of building everything that followed could finally begin. But the universe was still dark. For the next 100 to 200 million years there were no stars. Hydrogen and helium drifted through the void in enormous clouds pulled gradually together by gravity, growing slowly denser over millions of years. This period is called the Cosmic Dark Ages, not because anything was wrong, but because nothing was yet bright. The universe existed in patient, unlit silence, waiting for its first fires to ignite. When they did, everything changed. The first stars burned with an intensity we have never seen, since enormous, short-lived, brilliant objects containing hundreds of times the mass of our Sun, burning through their fuel in just a few million years before exploding in supernovae that scattered heavy elements across space. For the first time, carbon, oxygen, nitrogen, iron, calcium, all the elements that would one day be needed for planets and oceans and living things, forged in those first stellar furnaces and thrown into the void by those first cosmic explosions. From those ashes, second-generation stars formed, smaller, more stable, longer-lived. Around some of them, the scattered heavy elements clumped into planets. On at least one of those planets, chemistry organized itself into something that could replicate and adapt. And 4 billion years after that planet formed, the chemistry became complex enough to look up at the sky and wonder where it came from. We are in that moment right now. Astronomers call this the Stelliferous Era, the Age of Stars. It began with the first stellar ignitions roughly 100 to 200 million years after the Big Bang, and it will continue for approximately 100 trillion years into the future. 100 trillion years. Against that timescale, the entire current age of the universe, 13.8 billion years, represents less than 1% of the Stelliferous Era's total duration. We are not in the middle of the Age of Stars. We are in its early morning. But that era will end. The supply of hydrogen that stars consume is not infinite. Over time, star formation will slow. The galaxy will grow quieter, dimmer, cooler. New stars will stop being born as the raw material runs out. The existing stars will burn through their fuel and die one by one, leaving behind husks, white dwarfs, neutron stars, black holes cold and dark and silent. This is the degenerate era. It will last far longer than the Stelliferous Era, stretching across timescales of quintillions of years, numbers so large that our current age of 13.8 billion years would not even register as a rounding error. The universe will be an ocean of darkness, populated only by the slowly cooling remnants of dead stars drifting apart as space continues to expand. Eventually, even those remnants will fade. White dwarfs cool over incomprehensible timescales until they become black dwarfs. Objects so cold they emit virtually no radiation invisible, in every wavelength wandering through a lightless void. And then comes the black hole era. All that remains are the gravitational engines at the centers of dead galaxies, the supermassive black holes that once anchored entire civilizations of stars around them, now floating alone in darkness, so complete it defies any attempt at Prinzentennelos description. But even black holes are not permanent. Stephen Hawking demonstrated theoretically in 1974 that black holes slowly emit radiation, an infinitesimal trickle of energy produced by quantum effects at the event horizon. Over time, this radiation causes a black hole to lose mass. Imperceptibly slowly at first, then faster as the black hole shrinks until eventually it evaporates entirely in a final burst of radiation. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate completely. Write out that number, a 1 followed by 67 zeros. Now consider that the current age of the universe is approximately 10 to the power of 10 years. The evaporation timescale is not twice as long as the universe's current age, or 1,000 times longer, or 1,000,000 times longer. It is longer by a factor that the human mind cannot meaningfully process, and yet given enough time, even that process completes. After the last black hole evaporates, what remains? Elementary particles scattered across a space so vast and so cold that interactions between them become effectively impossible. No temperature gradients to drive reactions. No energy differentials to power any process. No information being processed anywhere. The universe reaches what physicists call heat-death maximum entropy, the state of perfect equilibrium where nothing can happen because everything is already as evenly distributed as it can possibly be. Not destroyed, just finished. Permanently and completely finished for a duration that makes the Stelliferous Era look like a camera flash. Now, place yourself back inside the present moment with all of that context in mind. We exist in the one narrow corridor of cosmic time when stars are burning, when the universe is old enough for complex chemistry to have had time to produce life, but young enough that the lights are still on. We can see across 93 billion light-years of observable space. We can detect the relic radiation from the universe's first 380,000 years. We can observe the large-scale structure of the cosmic web, study the properties of dark matter, measure the acceleration caused by dark energy. We can do all of this because we happen to be alive in the one phase of cosmic history when all of it is simultaneously visible and comprehensible. Beings born in the deep degenerate era, if any existed, would inherit a universe almost completely dark, with no way of knowing that it had once blazed with hundreds of sextillion stars. They would have no evidence of the cosmic web, no observable galaxies, no measurable expansion. They might conclude that their small, cold neighborhood of dead stellar remnants was all that had ever existed. We have the full picture, or as close to a full picture as any observer at any point in cosmic history will ever have. That is not nothing. That is extraordinary. If humanity somehow survived long enough to stand at the edge of the stelliferous era and watch the last stars dim and go cold, what do you think we would have become by then? What would consciousness look like after 100 trillion years of experience? We exist at the peak of cosmic complexity, the one moment in the universe's entire lifespan when things are complicated enough to produce awareness and transparent enough for that awareness to see where it came from. That seems like more than luck. That seems like something worth examining very carefully, because the next question is not about timing. It is about what we are actually made of and where those materials have been before they became us. There is a sentence that gets repeated often enough that it has started to lose its impact. You are made of stardust. People nod, find it poetic, and move on. But the poetry is not the point. The physics is the point. And the physics is stranger and more specific and more genuinely moving than the poetic shorthand suggests. Start with the carbon in your body. Every carbon atom in every cell of every tissue and organ you contain was not produced on Earth. Earth did not make carbon. Earth assembled it the way a construction site assembles materials that arrived on trucks from somewhere else. The carbon arrived here already made forged billions of years ago inside the cores of stars that no longer exist through a nuclear reaction called the triple alpha process, in which 3 helium nuclei fuse together under pressures and fest temperatures so extreme that the numbers describing them require scientific notation to write down. Those stellar cores maintained conditions that no laboratory on Earth has ever replicated, sustained by the gravitational weight of millions of times the mass of our Sun pressing inward from every direction. When those stars died, when they exhausted their fuel and could no longer sustain the nuclear reactions holding them up against their own gravity, they exploded. Supernovae so violent that for a brief period they outshone entire galaxies, radiating more energy in a single event than our Sun will produce across its entire 10 billion year lifespan. And in that explosion, all the material from those stellar cores, including all that carbon, was flung outward at a significant fraction of the speed of light, scattered across light years of space in every direction. Some of that carbon, after drifting through the interstellar medium for millions or billions of years, eventually became part of a new cloud of gas and dust. That cloud collapsed under gravity, forming our solar system. Most of the material went into the Sun. Some of it formed the rocky planets. Some of it landed on Earth, was incorporated into the geology, was absorbed by the first living cells, and has been cycling through living organisms ever since. Through bacteria, through algae, through fish, through dinosaurs, through mammals, and eventually through every cell of the body you inhabit. Right now. The carbon in your left hand and the carbon in your right hand may have come from different stars. They almost certainly did. Stars that lived and died billions of years before our Sun, ignited in regions of the galaxy that no longer exist in the same form, contributing materials to a cosmic recycling process so vast and so old that tracing any atoms complete, history would require reconstructing the biography of the galaxy itself. The iron in your blood is even more specifically earned. Iron is one of the few elements that can only be produced in abundance during the final moments of a massive star's life, specifically during the core collapse that triggers a supernova. In those last moments, iron accumulates in the dying stellar core, faster than any process can release it, until the core is so dense and so iron-rich that it collapses catastrophically, rebounding in the explosion that seeds space with. That iron, every hemoglobin molecule in every red blood cell circulating through your body right now, contains iron atoms that were forged in the death throes of a star. You are carrying the legacy of stellar catastrophe in your own bloodstream, the calcium in your bones, the phosphorus in the DNA encoding every piece of biological information that makes you specifically you, the oxygen in every breath you take. All of it assembled from debris scattered by stellar explosions across billions of years of cosmic history, swept up by gravity into clouds, compressed into new stars and new planets, dissolved into the oceans of a young Earth incorporated, into the first chemistry of life, and passed forward through an unbroken chain of biological inheritance, stretching back over 3.5 billion years to the very first self-replicating molecules. You are not a product of Earth. You are a product of the galaxy. Earth is simply where the assembly happened. Now look at something that researchers began studying seriously in recent years. Take an image of the large-scale structure of the universe, the cosmic web with its filaments of dark matter stretching hundreds of millions of light years, and its dense nodes where galaxy clusters gather at the intersections. Then place it next to a microscopic image of the neural network of the human brain, the neurons with their branching dendrites, the dense clusters of synaptic connections, the vast spaces between the active regions. The structural similarity is not vague. It is precise and mathematical. Both networks share the same ratio of dense nodes to connecting filaments. Both show the same distribution of void spaces between active regions. Both exhibit the same hierarchical architecture, where local clusters connect to larger clusters that connect to even larger structures. When researchers at the University of Bologna and the University of Naples measured this quantitatively, in 2020, they found that the number of connections per node, the clustering behavior, and the information density were strikingly similar across the two systems, one spanning billions of light years, the other spanning a few centimeters. This is not coincidence dressed up as metaphor. It is an observation about how complex networks self-organize, whether the medium is dark matter and gravity on cosmic scales, or neurons and electrochemical signals on biological scales. The universe and the brain arrived at similar solutions to similar organizational problems through completely different mechanisms across completely different scales. What that means at a deeper level is still being worked out. But it raises a question that goes beyond neuroscience or cosmology. If the same organizational principles that produce the structure of the universe also produce the structure of the organ that generates consciousness, is consciousness something that happens inside the universe, or is it something that the universe does? Is awareness a local phenomenon that emerges occasionally under the right conditions, or is it a property that the universe builds toward the way it builds toward complexity in every domain? Consciousness may not be an accident. It may not be a lucky byproduct of chemistry that happened to work out on one small planet around one average star. It may be the inevitable result of any physical system that grows large enough and complex enough and old enough, a pattern that the universe tends toward the same way it tends toward the formation of galaxies, the way it tends toward the emergence of stars from clouds of gas, not guaranteed in any specific place but inevitable at sufficient scale and time. If that is true, then every time you look up at the night sky and feel that particular combination of awe and smallness, that sensation of being an almost invisibly tiny thing, gazing out at something incomprehensibly vast, you are misreading the situation. What is actually happening in that moment is this: the universe is looking at itself. The atoms in your eyes that are receiving photons from distant stars are the same type of atoms as the atoms in those stars assembled from the same pool of raw materials by the same physical processes, organized by the same laws that govern everything from quantum particles to galaxy clusters. The looking is not separate from the thing being looked at. The observer and the observed are made of the same stuff, governed by the same rules, participants in the same unbroken physical process that has been running since the Big Bang. You are not a small creature peering into a vast and indifferent universe. You are the universe having organized itself in this particular corner into something capable of peering. The awe you feel is the universe recognizing its own magnitude through the temporary arrangement of atoms that you currently are. Every star that died to contribute its material to your body was not making a sacrifice in any meaningful sense. But the chain of events from those stellar deaths to this moment of awareness is real, and it is direct, and it is specific. Those supernovae had to happen. That carbon had to drift through space for millions of years. That particular cloud had to collapse into our solar system. That planet had to develop oceans. That chemistry had to generate the first cell. That cell's descendants had to survive 4 billion years of environmental change. And all of that had to converge in exactly the right way, at exactly the right time, to produce an arrangement of matter complex enough to sit here and recognize that it came from the stars. Does that make you feel smaller knowing you are assembled from ancient stellar wreckage? Or does it make you feel like something extraordinary, a temporary but genuine expression of a universe that has been working toward this kind of bit complexity since its very first moments? Both feelings are appropriate. They are not in conflict. And if consciousness is not an accident, if awareness is something the universe generates wherever it can, as reliably as it generates stars, then the question of how big the universe is takes on a completely different weight. Because the answer would not just be a number in light years, it would be a measure of how much awareness the universe has produced, how deeply it has learned to look at itself, and how far that process of self-recognition still has to go. And that answer is not something you will find in any physics textbook. It is somewhere else entirely. We started this journey in the most ordinary place imaginable, a night sky, a familiar ceiling of darkness scattered with points of light that human beings have stared at since before language existed. We looked up and asked a simple question: how big is all of this? What followed was anything but simple. We traveled from the solar system to the Milky Way, from the Milky Way to the observable universe, from the observable universe to the terrifying possibility that what we can see is a tiny fraction of what actually exists. We discovered that 95% of the cosmos is made of things science cannot identify or explain. We found that space itself is not a container, but a living fabric that bends, ripples, and stretches in response to mass and energy. We entertained the serious scientific possibility that our universe is one bubble among an infinite foam of other universes, each with its own physical laws, each permanently sealed off from all the others. We sat with the idea that the three-dimensional depth we move through every day might be a projection from a two-dimensional surface, and that everything we experience might be running on computational substrate we can never to examine from inside. And then, in the previous part, something shifted. We stopped measuring the universe from the outside and started recognizing that we are not outside it at all. The carbon in your body came from stellar cores. The iron in your blood was forged in dying stars. The atoms assembling your thoughts right now have traveled across billions of years and billions of light years to arrive in this particular arrangement. You are not a visitor to the universe. You are what the universe looks like from the inside, when it has organized itself into something complex enough to look back. Now comes the final question. After all of that, after all the numbers that defeated comprehension, and all the theories that unsettled every assumption, what is the actual answer? How big is the universe begin with infinity, because infinity is where the mathematics keeps pointing, and infinity is almost always misunderstood. Most people, when they hear the word infinite, picture something very large, larger than a galaxy, larger than the observable universe, larger than any number they can name. They imagine infinity as a number at the end of a sequence, the biggest possible thing sitting at the far end of the scale after all other sizes have been exhausted. But that is not what infinity is. Infinity is not a large number. Infinity is the absence of any boundary on number itself. And that distinction, seemingly academic, has consequences that are genuinely destabilizing once you follow them honestly. Consider this. If the universe is truly infinite in extent, then the distance from where you are sitting right now to the nearest wall of your room is exactly the same proportion of total space as the distance from Earth to the most distant galaxy ever. Observed, both distances a few meters and 46 billion light years represent precisely 0% of infinity. Not a small percentage, not a negligible percentage. exactly mathematically 0%. They are identical in their relationship to the whole, which means that in any meaningful cosmic sense, the distance to the wall and the distance to the edge of the observable universe are the same. Both are nothing. Both are local. Both are so vanishingly small relative to the totality of space that no instrument, no mathematics, no concept of proportion can distinguish between them. This is not a philosophical trick. This is what infinity actually means, and it applies to everything we have discussed. Every number we have used across this entire journey, the 100,000 light-years of the Milky Way, the 93 billion light-years of the observable universe, the 23 trillion light-years of the estimated minimum real universe. Every single one of those numbers, if the universe is infinite, occupies exactly 0% of the total. They are all local. They are all in the only scale that matters the same size. Infinity does not dwarf the universe. Infinity dissolves the concept of size entirely. Now consider what this implies for knowledge. Every major discovery in the history of science has followed the same pattern. A question is asked, an answer is found, and the answer, without exception, reveals a territory of new unknowns vastly larger than the question that prompted the search. When Newton described gravity mathematically, it was a triumph of human understanding. It also revealed that the motion of every object in the universe was governed by forces that operated across empty space with no apparent mechanism. A mystery that took 2 more centuries and Einstein's general relativity to partially address. When Einstein's equations were confirmed, they revealed space-time curvature and black holes and gravitational waves and the expanding universe, each a new world of questions. When astronomers measured that expansion and discovered it was accelerating, they found dark energy, an unknown force making up 68% of everything, which remains completely unexplained today. When quantum mechanics was developed to describe the behavior of particles at the smallest scales, it revealed superposition, entanglement, and wave function collapse. Phenomena so strange that the physicists who discovered them spent the rest of their lives arguing about what they meant. Every door opened onto a hallway containing more doors than the room that came before. Every map completed revealed a larger, unmapped territory surrounding it. This is not a feature of our current incomplete state of knowledge, something that will eventually be resolved when science matures enough. This appears to be a structural property of reality itself. The universe is not a finite puzzle waiting to be solved. It is a depth that increases with every level of examination in every direction without apparent bottom. And consider what that means for curiosity. In a universe that could, in principle, be fully mapped and fully understood, a universe with a finite number of facts to discover, curiosity would eventually have nothing left to do. The project of understanding would complete. The last question would be answered, and consciousness, which exists precisely because it is driven to explore and understand, would find itself with nowhere to go. The universe we actually live in does not permit that outcome. Every answer generates more questions. Every discovery increases the known unknown. The territory of mystery does not shrink as knowledge advances, it grows, because understanding gives you the ability to perceive complexity that was previously invisible to you. The more you know, the more clearly you can see what you do not know. Ignorance is not the absence of knowledge. It is what knowledge makes visible. This is not a flaw in the design of reality. It is the feature that keeps consciousness in motion. The universe appears to be constructed so that awareness always has somewhere further to go, something more to understand, some deeper level of structure to discover. Curiosity does not become obsolete in this universe. It becomes more necessary with every generation. Now look at the relationship between consciousness and the universe across time. 100,000 years ago, human consciousness was aware of an immediate physical environment, the landscape within, walking distance, the patterns of seasons, the movements of animals. The known universe was the visible horizon. 5,000 years ago, awareness extended to trade routes, to the movements of civilizations, to the patterns of stars used for navigation. The known universe was a continent, a sky, a set of mythologies that organized the whole into a comprehensible story. 400 years ago, Galileo pointed a telescope at Jupiter and saw moons orbiting another planet. The universe expanded overnight from the visible sky to a solar system. 100 years ago, Edwin Hubble demonstrated that the fuzzy patches of light, called nebulae, were not clouds within our galaxy, but entire separate galaxies, island universes, each containing billions of stars scattered across a space. So vast that our own galaxy was revealed as a single grain in an incomprehensible collection. The universe expanded by a factor of billions in a single decade. Today we are measuring the cosmic microwave background radiation with enough precision to constrain models of inflation. We are detecting gravitational waves from black hole mergers a billion light-years away. We are photographing the first light of galaxies that formed when the universe was only 400 million years old. The known universe has expanded again and is expanding still. Each expansion was not just a change in the numbers, it was a change in what consciousness was capable of holding. The awareness that could navigate by stars was genuinely different from the awareness that could not. The consciousness that understood galaxies was genuinely different from the consciousness that understood only our own. Every expansion of the known universe was simultaneously an expansion of the kind of mind that could contain it. Consciousness and cosmos grow together. The universe becomes more complex, and awareness develops the capacity to perceive that complexity. Awareness perceives the complexity and develops the tools to probe deeper, revealing more. The loop has no obvious closing point. It is not a circle. It is a spiral moving outward in both directions simultaneously, the universe growing in what is known of it, the consciousness growing in its capacity to know. Which brings everything back to the question that opened this journey. How big is the universe? The honest answer is that this question does not have a fixed value waiting to be measured. It is not asking about a static property of an independent object, the way you might ask about the diameter of a coin or the mass of a planet. The universe is not sitting still waiting to be measured. It is changing, expanding, evolving, and so is the consciousness attempting to measure it. The question is not about a thing. It is about a relationship, an ongoing, dynamic, deepening relationship between awareness and the reality it finds itself embedded in. The universe is exactly as large as consciousness has developed the capacity to recognize. Right now, that means 93 billion light-years of observable space, 2 trillion galaxies, a cosmic web of dark matter filaments spanning structures 500 million light-years across a multiverse that may be infinite, a holographic surface that may encode everything we experience, a history, 13.8 billion years long, and a future stretching to heat death across timescales that dwarf every number we have used in this conversation. That is how big the universe is right now, measured against the current capacity of human awareness to perceive and comprehend it. But future consciousness, human or otherwise, will have a larger answer. Not because the universe will have grown, though it will have, because awareness will have grown to see what is already there, waiting beyond the current edge of comprehension. And you sitting exactly where you are in this moment are not a small creature lost in the vastness of that space. You are the point where 13.8 billion years of cosmic evolution has converged into something capable of asking the question. Every supernova that seeded the galaxy with heavy elements, every billion years of geological time that allowed complex life to emerge, every generation of living things that passed biological complexity forward through time, all of it culminates here in the awareness that is reading these words and reaching towards something it can almost but not quite fully grasp. That reaching is not a limitation. It is the whole point. Go back now to where we started. A night sky. The same darkness, the same scattered points of light. You looked up then and felt something, some combination of wonder and smallness and strange comfort that is difficult to name precisely. Look up again. But look, with everything this journey has given you, those lights are not distant and cold. They are your origin. The carbon that processes the photons entering your eyes came from stars that burned and exploded in regions of the galaxy that no longer exist in the same form. The iron carrying oxygen through your blood was forged in stellar cores under conditions we cannot replicate on Earth. Every atom you are made of has been part of that. Sky has drifted through the void between stars, has been swept up by gravity and compressed into new forms again and again across billions of years until this particular arrangement came to to exist temporary, specific, and aware. The light reaching you from a star 2,000 light-years away has been traveling since before any civilization on Earth developed writing. It crossed interstellar space, survived the journey across an unimaginable void, and arrived at your eye in this precise moment. That is not background scenery. That is the universe delivering a message across 2,000 years of transit time, addressed to whatever awareness happened to be looking up at the right moment. You are the right moment. The universe is not big in the way a warehouse is big, or the way a country is big, or even in the way a number can be big. It is big in a way that exceeds the category of bigness entirely. Big in a way that the concept of measurement begins to fail when applied to it. Big in a way that infinity is not merely a description of its size, but a description of the relationship between its depth and any mind that tries to contain it. And you are big enough to hold that. Not completely, not finally, but enough to reach toward it, to feel its weight, to be genuinely changed by the attempt. After everything, the supernovae and the holographic principle, the dark matter and the dying stars, the cosmic web and the heat death, and the multiverse, what is the one thing you will carry with you the next time you look up at the night sky? The universe is exactly as large as consciousness can stretch to recognize it. And consciousness, as we have followed it from the first moment of the Big Bang to this present instant, turns out to have no fixed ceiling, no final limit, no point at which it has reached as far as it can go and must stop, which means the universe, measured the only way that has ever truly mattered, may have no limit either.